Okay, please.
Okay, so yeah, well, thanks for inviting me to talk. Um, so I guess I'm going to be talking about the generalized scalar potential. Um, and maybe I'll list a couple of relevant references for what I'm going to speak about. One of them is a paper by Marco that he wrote probably over 10 years ago, which is called Brains on Poisson varieties. And then the other one is our paper called Morita equivalence and the generalized scalar potential. So this is with Marco and also Maxime Zabzin. And there's also my thesis, which is called Morita equivalence and generalized scalar geometry. Apart from the thesis being kind of maybe more detailed than the paper, it also so in the paper we use kind of the technology of Courant algebroids and Dirac structures to kind of derive some of the results. Whereas in my thesis, I do it just kind of using kind of tensor manipulations and so on. So depending on what your preference is, you could look to one or the other reference. Okay. So for the first part, guess I'll talk a little bit about what happens in the case of Kähler geometry. So I'll just recall the Kähler potential. So for this, well, let's start with a Kähler manifold. I'll just write it M, G, I, omega. So here, G is a Riemannian metric. I is a complex structure such that G is Hermitian. And because of this fact, we can combine the metric and the complex structure to get a 2 form. And this thing has to be closed. And the fact that the metric is Hermitian, it translates to the form actually being of type 1, 1. So what this implies by the kind of the local DD bar lemma, it says that on a small open set, there exists a real function. So it's a smooth real function such that on this open set, the Kähler form is I dd bar times k. So this function here is called the Kähler potential. I'll just comment a little bit more on what the meaning of the Kähler potential is. So, so something that we can do is if the cohomology class, so initially, if we take the cohomology class of the Kähler form, it's real and it has type 1, 1. But if it's in the image of the integral forms, then it can be pre-quantized. So what this means is that there exists a pre-quantization. So what this is that U is a holomorphic line bundle on M. H is a Hermitian metric. And nabla is the Chern connection. So this is the unique Hermitian connection such that if we take the 0, 1 component, so the 0, 1 component of the connection, it allows you to differentiate sections of U by 0, 1 vectors. And we want this thing to be the Dull bar operator on section, meaning that holomorphic sections are defined by the fact that if we apply this operator, they vanish. And so all of this structure, for it to be a pre-quantization, we want that the curvature of the connection is essentially equal to the symplectic form. So then, given a non-vanishing section, non-vanishing holomorphic, well, we get a Kähler potential. What we can do is we can define K to be some factor times logarithm of the norm squared. So this is the norm squared with respect to the metric. So this gives a Kähler potential. And you can kind of think that the metric, the Hermitian metric, in the case that the symplectic form is pre-quantizable, the metric kind of gives a global meaning of the potential. So of course, if we vary the section to another holomorphic section, they differ by a holomorphic function. And so the difference between K, if we add in a function, say we replace S by F times S, where F is a holomorphic function, then K would get replaced to K, I guess, minus 2 pi logarithm of, well, F squared, which is harmonic, I guess. Okay, so that's the story for Kähler geometry. Are there any questions about this so far? So essentially, we want to generalize this to the setting of generalized Kähler geometry. So let me, I'll write a couple of questions. Well, kind of vaguely, it's what are the analogs of these things for generalized Kähler geometry? So maybe one way of asking the question is, what are the degrees of freedom in generalized scalar geometry? So the way that this would be answered in the Kähler case, so we have kind of these three structures, but they're kind of all related in a certain way. And I mean, essentially the kind of the moduli of Kähler structures, it comes down to the complex structure. That's like the holomorphic structure that you can vary. And then on top of that, you have this kind of extra degree of freedom, which is the metric, which essentially comes down to a function. At least locally, it's a function. And I guess if we want to vary it, we can vary it using a function. I mean, if we stay in the same Kähler class. So that's one potential question. Another question is there something like a generalized Kähler potential? So this is a question that was asked, I think, even in the original papers in 84 of Gatesall and Rocek. I mean, I think they, for certain examples, they already had potentials. And so that this was a question of how to generalize this. And then a third question is, what is the kind of the pre-quantization or even quantization for generalized scalar structures? Yeah, so I'm going to try to answer at least the first two. Maybe I'll get to the third one as well. Okay, so okay, so the story that we covered for the generalized scalar potential, it applies to a certain subclass of generalized scalar structures, which are called generalized scalar of symplectic type. So I think one of Marco's students is working on a general case. So yeah, it would be interesting to hear about that in the future. But yeah, so I'll discuss what happens in this case. And I'm going to maybe start by just recalling the definition of generalized scalar structure. So one of the kind of slightly confusing things about this subject is that there's so many different equivalent definitions. And we've already seen two, which I'll recall. And then I'm going to give a third equivalent definition, which will be the one that I want to use for the rest of the talk. So the first one is version 1, which is the one from that the physicists gave, I think, which is that a generalized scalar structure, it consists of the data of the following: gi plus I minus, where g is a Riemannian metric, I plus and I minus are complex structures. So we have two complex structures, but for which G is Hermitian with respect to both. And it satisfies an integrability condition. So if we define omega plus minus to be the associated Hermitian forms, so these are two forms, then these satisfy the following equations, which are I guess the generalization of the fact that the two form in a Kähler structure is closed. They're in this case, they're not closed. They satisfy the following equation. So first of all, dc plus omega plus dc minus omega minus is 0. So here, dc, it's an operator. It's a real operator, like the Durham differential, but it's a different one that you get when you have a complex structure, and it's defined as del bar minus I times del bar minus del. So remember, d is del plus del bar. So dc is I del bar minus del. And since we have two complex structures, we have two of these operators. So that's the first equation. So that's essentially saying that, well, if given omega plus and omega minus, we can take a dc of them to get a 3 form, and it's essentially the same form if we do it for omega plus or omega minus. And then the second condition is that d of d plus, either plus or minus, is equal to 0. So if you remember in the previous talks that Marco gave, there was this 3 form that was kind of relevant, and that one is it's exactly this d plus c omega plus. Okay, so that's the first definition. There's the second version, which was that a generalized Kähler structure it consists of a pair of commuting generalized complex structures. Remember, these act on T plus T star. And so a generalized Kähler structure consists of a pair of these that commute, and such that if we take their product, we get a generalized metric. And what that means is that if we use the natural inner product on T plus T star, and we combine it and we combine it with G, then this is positive definite. And if you remember, the way to go between the two definitions kind of involved this picture. So here we have T, here we have T star, and then we had these two subbundles, C plus and C minus. So this is where C plus is where the metric is positive definite, and C minus is where it's negative definite. And on C plus, JA is equal to JB. And on C minus, JA is equal to minus JB. So we get a complex structure on both C plus and C minus, and C plus and C minus, they project isomorphically to T. And so in that way, we get kind of transported to the tangent bundle, I plus and I minus. So that's, and I guess the graph, C plus minus is something like the graph of the metric plus or minus b? No, like this. So that's one direction. And then the other direction, there's just a formula for going back. So you can do either JB or JA. And that's given by the following formula. So I'm going to write both JB and JA. They're going to be the same formula but differing by signs. So for JB, it will be plus I plus I minus, and for J, it will be with a minus. So the top will be B, the bottom will be A. Actually, the formula that I've given here, strictly speaking, it's for B equals to 0. But I guess it's not an essential feature that I want. I just want to give the general formula. Yeah, so this is basically just the way that if you just have all of the structure on the tangent bundle, then this is how you reconstruct the two generalized complex structures. And here, omega plus minus, these again are these Hermitian forms. Okay, so now I can give the definition, which is that a GK structure is of symplectic type if omega plus plus omega minus is invertible. Okay, so that's the definition. So the reason I kind of recalled this formula is because I want to explain what this condition means. So if we look at the top corner of JA, so remember JB, I'm just going to move this down. So the generalized complex structures, you can think of them as mapping. So they're mapping from T plus T star. We can write kind of on the top and on the side. So this component here, this is the part that goes from T star to T. So you can think of this in the following way. We have T star, which is included in T plus T star. Then we can apply J, say A in this case. And then we project to T. And this composition, where I put in JA, is exactly this top corner, which would be minus omega plus minus 1 plus omega minus 1. And I guess the fact, I think Marco discussed it last time, that this map, which is the top corner, it's kind of invariant. It's an invariant structure that doesn't depend on the B-field transformations, and it's a Poisson structure. So this here, it's a Poisson structure. And let's actually use this formula here to write it out. So what we get is that it's equal to Well, it actually is just equal to I plus I minus times G inverse. So the fact that that I plus I minus is invertible is equivalent to the condition that this Poisson structure here is invertible. So what that means is that we get a symplectic form, because an invertible Poisson structure gives rise to a symplectic form. So we get a symplectic form, which is the following. This is symplectic. And furthermore, so because the Poisson structure of the GC structure JA is actually symplectic, that means that up to a gauge transformation, JA is just equal to the GC structure of a symplectic form. So that's the reason for the terminology. So a generalized scalar structure is of symplectic type when one of the generalized complex structures is actually symplectic. But when we phrase it in terms of this bi-Hermitian picture, the version 1, it translates to the condition that I plus I minus is invertible. And so for what I want to talk about, this first version is actually kind of more useful. So that's why I wanted to translate it to this form. Okay, so
wait, Francis, just so I'm sure I understand, the general statement is if I have a generalized complex structure where the associated Poisson structure in the upper right block is invertible, then there's always a B field transform that puts it in this canonical form.
mhm.
And I guess you, oh, I see. Okay. Yeah.
Yeah, that's right.
Okay.
Okay, so for the next thing I want to talk about is the connection to Poisson geometry. So yeah, we've already seen. So by the way, I'm later on, I'm going to say a little bit more about Poisson geometry for those who aren't familiar with it. At the moment, I wasn't going to say too much, but if there's anything that I need to explain more, just interrupt me. You're right. So we already saw that a generalized complex structure, they have associated real Poisson structures. So that's what I just mentioned here. Okay. Oops. For generalized scalar structures, they also have Poisson structures coming in, but in a different way. So this is something that was first observed by Hitchin, which is that generalized scalar structures, they have associated holomorphic Poisson structures. So this is sort of interesting how it works. So first of all, we can define the following tensor. So we're going to take the commutator of I plus and I minus and compose it with the metric. So this is something that goes from T star to T. And it's a fact that Hitchin shows is that this is a real Poisson structure. But in fact, more is true if we define these sigma plus and minus in the following way. Like this. So we just, yeah. So these things, this is the theorem of Hitchin again, is that sigma plus or sigma minus is a holomorphic.
Francis, I think something went wrong with the screen. At
Oh,
least
really?
for me, it stopped in the middle of the line defining sigma plus minus.
Oh, yeah, it's frozen. Oh, is it back?
Yeah, there. Yeah.
Okay. It might just be the connection. Hopefully it's okay. Right. So the theorem of Hitchin says that this sigma plus minus, this is a holomorphic Poisson structure with respect to I plus or I minus. So what I mean is that you can do this either for I plus or you can do it for I minus. So you get these two tensors, sigma plus and sigma minus. And sigma plus is a holomorphic Poisson structure for I plus, and I minus is a holomorphic Poisson structure for I minus. So it's kind of interesting if we just start with a generalized Kähler structure, we actually get these two holomorphic Poisson structures. And these holomorphic Poisson structures, they're interesting because they're measuring the failure of the two complex structures to commute. So, if we're in a Kähler case, this is not going to show up because I plus is equal to I minus. So in this case, the Poisson structure is 0. So that's why we don't see any of this in the Kähler case. But when we move away from Kähler geometry to generalized Kähler, then we get this interesting Poisson geometry. And sigma plus and sigma minus, they can be sort of different. They don't, like, if we consider m I plus and sigma plus and m I minus sigma minus, these need not be isomorphic. So you could have genuinely different Poisson structures on the same smooth manifold, and which are both part of the same generalized Kähler structure. So they're not isomorphic, but they do have the same imaginary part. Okay, and so I guess so far we have a whole bunch of tensors. It's like an explosion of tensors.
Is there, Francis?
Yeah.
Is there a relation between sigma plus minus and the previous Poisson structure, the one that any GC structure has?
Yes. So if we look back, so these ones, the other Poisson structures, they're kind of coming from I plus I minus times G inverse. And the other one would be with the minus sign. Let me just say like JA gives you I plus I minus G inverse, and JB gives you I plus minus I minus G inverse, up to a sign and some constants. So these are two different Poisson structures, and this one here, Q, is with the commutator. But let me just make an observation here, is that the commutator of these two things, you can actually rewrite it as a product. Like this. So what this means then, is that the image of Q, like viewing Q as a map from T star to T, what you can see here is that the image of Q is the intersection of the image of, I don't know, I'll call this one PA and this one PB. So by the way, this is true even when like I just said we restrict to the case where PA is invertible. I mean, this is true even when PA is not invertible. So the image of Q is the intersection. And so what this means is that like PA, it's a Poisson structure, so it gives you a foliation in terms of symplectic leaves. PB gives you another foliation in terms of symplectic leaves. And if you intersect those symplectic leaves, those give you the symplectic leaves for Q. So they're definitely related. And you can say more if you use Dirac structures to say how they're related, but I think it's a little bit subtle how they're related, I think. I mean, it's not completely obvious, but this is at least one thing that you can directly see, that symplectic leaves of Q is the intersection of the symplectic leaves of the two other. Right. So, okay. So I just want to recall this. I just want to keep this fact. It's kind of useful. So we'll just keep it there. So yeah, so far we have all of these different tensors, G plus, or GI plus, I minus, F, which was, if you remember, minus 2G I plus I minus inverse. And then we also have Q. And I guess then we have sigma plus and sigma minus. Okay, so we have all of these tensors, and they're definitely not independent. So there's a bunch of interesting compatibilities between them. So let me just say a couple of them. So the first is that we could take Q. So Q is a map from T star to T, and F, it's a symplectic form, so it's a map from T to T star. So we can compose them. So we could take Q, compose with F. And well, if you look at what's going on here, so Q is going to involve the product of I minus I plus, I minus plus I plus, and then G inverse, and then F is going to involve G and then I plus plus I minus, but inverse. So the G's are going to cancel, and also the I plus I minus inverse is going to cancel with the I plus I minus. So what we end up with is the following. It's just kind of simple. And then the second one, well, G is Hermitian with respect to both I plus and I minus. And we've kind of formed F by kind of combining the two. So the fact that G is Hermitian, it implies that F satisfies what's kind of like a joint 1-1 condition, which is that Fi plus I minus F is 0. So, I mean, if I plus would be equal to I minus, which would just be a single complex structure like we have in the Kähler case, then this would say that F is 1-1, like a 1-1 form, which is, I mean, in the Kähler case, F just would be the Kähler form, which is 1-1. But when we're in a generalized Kähler structure, F satisfies this kind of slightly different condition, which is like the 1-1 condition, but it involves both of the complex structures. Okay, so look at so we have all of these structures and they satisfy these compatibility conditions. And essentially the result that I want to state, which is due to Marco in his paper on branes and Poisson varieties, it says that a generalized scalar structure of symplectic type is equivalent to the data of, well, the following structures. The two complex structures, this real Poisson structure Q and F, where I plus and minus are complex structures. Q is a Poisson structure, which is the common imaginary part of two holomorphic Poisson structures with respect to I plus and I minus. And F is a closed two form. And then they have to satisfy some compatibility conditions. And the compatibility conditions are exactly these ones that we've observed above. So first one is that I plus minus I minus. The difference is given by QF. And the second one is this joint 1-1 condition. And finally, well, when we have all of this structure, we can form a symmetric tensor and we want this thing to be positive definite. Okay, so I'm just going to copy this for the next page. Okay, so this is like the kind of the important result, which means that we can, instead of thinking about generalized scalar structures in the other two versions, we have a new formulation of it. And this is the one that's going to be useful for what I'm going to talk about. So it's kind of maybe an annoying feature that for different things that you want to understand about generalized complex or generalized scalar geometry, you need to switch to a new definition, but that's how it is. And yeah, so this condition on G is called positivity. Well, sometimes we say positivity of F, even though it also involves I plus and I minus. And it makes sense to relax this condition. So we could consider also we could define something that's called a degenerate GK structure, where we have everything except for the condition that G is positive definite. So we can relax this. And this is useful because it gives new examples, and those examples, I mean, even if we only care about the case where G is positive definite, the other examples which don't satisfy this can still be useful maybe when we're trying to construct new examples. So here's a really basic example. Just let Mi sigma be a holomorphic Poisson structure. Then Q0 is a degenerate GK structure. Okay, are there any questions about this? Okay, so
Can
I
you
wanna-
go back to the example one more? So, okay. Okay.
So
Yes.
I'm just saying that this triple, quadruple, whatever, IIQ0, it satisfies both these conditions in a trivial way.
Right.
But then there is no metric; it would just be 0. But it's still useful to maybe include this because you can, well, as I'm going to discuss next, you can kind of deform away from it to actually get something where the metric is positive definite. Okay, so this is the flow construction, which is about deforming into GK. Well, this both gives methods for taking a generalized scalar structure and deforming it, or taking just a holomorphic Poisson structure and deforming it into a generalized scalar, or taking a scalar and deforming it into a generalized scalar. So it's quite general, and it was mainly developed by Hitchin and Marco. Okay, so the starting data for this construction is the following. So first we have a holomorphic Poisson structure. Xi sigma Second, we have a Poisson vector field. So this means that it's a vector field such that if we differentiate Q with respect to V, we get 0. So it's, I guess it's a Poisson vector field for the imaginary part, so for Q. And then the third structure is a real closed 1-1 form, omega. And it has to satisfy a compatibility condition, which is that if we take the lead derivative of a complex structure with respect to this vector field, this is given by Q composed with omega. And then here's the construction. Well, we take the flow phi sub t of V, and then we define an averaged 2 form, F sub t, so it's time dependent. So we essentially pull back omega by the flow of V and average it. And then we just take I minus to be the given structure I, and for I plus, we take the pullback of I. So a theorem, so this is again due to Marco in the Brains paper, Brains on Poisson variety. It says that I plus, I minus, ft, q, or I think maybe I wrote q first. This defines a, well, possibly degenerate GK structure of symplectic type. So what's going on here? Well, we want these equations to be satisfied here. And so I'm just going to copy them. This equation here, oops, this one here is the infinitesimal version of this one here, right? Because this is like I of t minus I of 0 is equal to q times f of t. So this equation is the integrated version of this one. And this equation, which is this joint 1-1 condition, it comes from the fact that omega was closed. So that's essentially the reason why this works. We've just kind of written the infinitesimal version of these two equations that we need to satisfy. Okay, so this here, it might not be. Oh, let me say also, one way of thinking about this is that the thing that we've started from is exactly this kind of trivial degenerate structure, right? That's what we get at t equals to 0. So I plus depends on t as well. So we're really deforming away from that. So if omega is scalar and t is small, then we get a genuine GK structure. And another way of rewriting this, so we can again take same I plus and I minus, but remember the equation that I plus I minus Q and F needs to satisfy, it involves the product of Q and F. So what we can do is multiply Q by T and divide F by T. So this also gives a solution. And I just want to point this out because in this case, when T goes to 0, this part goes to 0, and this part goes to just omega. So we can either view it as deforming from this kind of Poisson structure without any metric or anything, or we can view it as deforming away from a Kähler structure by kind of turning on a Poisson structure. There's these two perspectives that we can take. Okay, so I want to give a couple of examples of this.
Wait, sorry, Francis. Can you go back to the previous page?
Yeah, sure.
And maybe can I see all of it? Yeah. I mean, I guess you're defining it as flowing away from this sort of degenerate, purely like Poisson tensor example.
Yeah.
But somehow it's the same from a symplectic type GK, I guess.
What do you mean?
What do I mean? So
what I was saying is that
sorry, I guess I guess since so sort of at time 0 the two complex structures are the same, so it would just be Kähler if you start with symplectic type.
I have a question, if I may.
Yeah.
Yes. What happens if I just start with already one generalized scalar of symplectic and I try to deform that way the given one? I just take omega be DDC of a function and just do this to one of the, let's say, to E minus.
Yeah. So that's going to be one of my examples. Yeah.
Okay.
So yeah, there's many different ways that this can be applied. And I just wanted to point out here, one of the things is that just given this construction, here we've kind of applied it to just a holomorphic Poisson structure. and this gives a GK structure. And there's already two ways of seeing it. There's this family, which gives you a family of these degenerate GK structures, and there's the second family. They both solve the equation. This top one, when we send t to 0, it gives us one of this sort. And in this one, when we send t to 0, it gives us I 0 omega, which is a Kähler structure. So you can kind of view, say that t equals to 1 as a deformation either of a Poisson structure or of a Kähler structure. But yeah, if you already have a generalized Kähler structure, you can apply the flow construction to one of the complex structures with its Poisson structure, and that will give you a deformation. So I'm going to talk about that in a second. I want to give just the most basic example first, which is, I'm going to start again just with a Poisson structure, holomorphic Poisson. The question is, of course, how do we produce these structures, the vector field and the real closed form that satisfy this equation? So one way of doing it is quite simple. We just let f be a real function. Then we take v to be the Hamiltonian vector field, and we take omega to be essentially dd bar of a function. So this defines the data. Needed to run the flow construction. Okay, so yeah, so this can be applied to a given GK structure to deform it. So I want to give a specific example of this, which I think is due to, it's in a paper of Apostolov, Goduchon, and Grancharov. And from my understanding, it also kind of came from a suggestion of Dominic Joyce. I don't know is that correct?
Yes, it's correct.
So here's the example. So let's start with a hyperkähler structure. So this is like we have a pair of 3 Kähler structures and ij is equal to k. So this gives a generalized Kähler structure. Where we take I plus to be I, and I minus to be j, q to be omega k inverse, and f to be omega I plus omega j. So this is a generalized Kähler structure of symplectic type. In a sense, it's a very symmetric one, right? Because we can kind of rotate to get a whole bunch of different generalized Kähler structures. But what we can do is we can kind of break the symmetry by deforming away. So if we can take this function f that we had above, and I guess, okay, so f be a real function, and define v to be omega k inverse df, so it's the Hamiltonian vector field, and phi sub t is the flow. Then we get a new non-hyperkähler GK structure, which is for I plus, we take the flow of I. For I minus, we keep J. For Q, we keep omega K inverse. And then for F, we take omega minus plus omega j minus, so it's again this integral of dd bar of f. And here the del and del bar operators are with respect to the complex structure I. And you can check this. This is actually, you can rewrite it as follows. So it's omega I plus the flow of omega j. So this is a way of starting with a hyperkähler structure and deforming into a non-hyperkähler generalized scalar structure. Okay, I want to give a second example. So for this, the starting data of the complex structure is going to be a complex projective plane, CP2. For the holomorphic Poisson structure, so the holomorphic Poisson structure is a holomorphic bivector field. So it's a global section of H2, a global section of wedge 2 of the holomorphic tangent bundle. So this is, since we're on CP2, this is actually the anti-canonical bundle. And on P3, the anti-canonical bundle is O3. So we just take a global section, a global bivector like this, and if it's smooth, it will vanish on a cubic curve. So what I've drawn in black, let me draw it in red. This is where sigma is equal to 0. Okay, so that's the Poisson structure, and then for the 1-1 form, we take the Fubini Studi Kähler structure. Okay, so we need to produce a vector field. The way that we can do it is as follows. So sigma is H0 of wedge 2t. Omega, we can write it as an element of H1 of omega 1. So that means that if we combine sigma and omega, and I mean, take the cohomology class, then this omega 1, this one form part will hook into the bivector field and give a tangent vector component. So this is going to be an element of H1 of t. And for CP2, for the complex projective plane, this is 0. So this is because this is this homology group. It classifies the infinitesimal deformations of CP2, and this is 0 because there are no deformations of CP2. And so there exists a vector field V such that it's going to be say a 1-0 vector field such that d bar is equal to omega, sigma applies to omega 0. So this is essentially this property here. Okay, so I claim that it's possible to choose V so that it's also a Poisson vector field. The way to do that is what's kind of nice. We actually can use sigma itself to do it. So here's what we can do. So consider so so we can choose a metric on the canonical bundle such that the curvature of the Chern connection is going to be 6 pi I omega 0. So omega 0 is for omega 0 is the curvature of the Chern connection on O1, and this is O minus 3. So that's why we get this relation. Then let omega be sigma inverse. So this is a section of the canonical bundle. It's singular. It's singular exactly on this elliptic curve, this red vanishing locus. But in any case, what we can do is we can apply this Chern connection to omega. And this will look like a 1-0 form tensor omega. And because the curvature of this connection is 6 pi I omega, that means that d bar of alpha 1-0 is 6 pi I omega 0. So then we can take V to be sigma applied to alpha 1-0. So this, even though alpha was singular, this will be smooth. So this is smooth. It's Poisson, and it satisfies okay, so that's how we do it. Okay, so we've produced the kind of the input for the flow construction, and then we run the flow construction, and we get this generalized scalar structure. Okay, so this gives a GK structure.
Can you go back to the previous slide? So what is the claim? So your sigma is the initial holomorphic Poisson structure.
Yeah.
And then you are taking omega to be the sigma minus 1. What you mean, like omega is sigma minus 1?
Oh, this one here.
Yeah.
Yeah. Yeah, because right, because sigma is a section of K inverse, so omega is like the symplectic form that has poles along the.
Okay, but you're not claiming that this is a. Okay, so it's just some singular holomorphic symplectic form. Okay.
That's right. So that's the interesting thing. So yeah, so this is singular, and so alpha 1-0 is singular, right? But when we apply sigma, the singularities cancel out because alpha 1-0, it has a pole along this red curve, this elliptic curve, but that's exactly where sigma vanishes, and so they cancel out.
Okay.
And so that cancellation, I mean, is sort of like by direct construction. I mean, you just know you're computing the derivative of the fact that it's coming from the derivative of sigma inverse.
That's right. Yeah. And I think it's sort of, I'm not 100% sure about this, but I think the fact that it's not going to vanish means that it will actually deform the vanishing locus.
So you said that it will deform.
No, it actually, I think it can't. Never mind. Yeah, it can't deform it because the two Poisson structures that we get at the end will have the same. They'll have the same imaginary part of the Poisson structure. I guess it will flow probably along it, I guess. Because the output at the end is we get a generalized scalar structure such that sigma minus is sigma. This vanishes on this elliptic curve, sigma plus also has to vanish on the same elliptic curve. Okay. And I just want to make a remark here, which is that in all the examples, well, the way that we've done the deformation, we've deformed the complex structure with a diffeomorphism. So that means that the complex structure that we get at the end, mi minus, is isomorphic to mi plus. And this isn't true when we've deformed, when we deformed the hyperkähler, it started off where the two complex structures were not isomorphic. But when we deform away from this Poisson structure, the two complex structures will be isomorphic. But it's possible to also extend the flow construction so that it also deforms the complex structure. So when, for example, sigma omega is not 0, and this is not 0, so we can't run the flow construction as we've stated, but it's a theorem of Hitchin that this direction is unobstructed. So we can deform the complex structure. Yeah.
You refer to the Gotthel's theorem or Hitchin? I'm a bit confused.
Well, I think there is also a theorem of Goto about deforming, but I'm referring to, there's a theorem of Hitchin. It's a paper, Deformations of Holomorphic Poisson manifolds, where he shows that under some assumptions on some cohomology groups, that this direction is unobstructed, so you can deform the complex structure. And then Marco showed in a paper that you can lift this. The deformation of the complex structure can be lifted to a deformation of the generalized scalar structure. I think that's right. So the paper that where it's described is called Generalized Scalar Metrics from Hamiltonian deformations. But there is also this a theorem of Goto, which is about unobstructedness of deformations of generalized scalar structures.
And the statement of Hitchin is that it's just if you have a Poisson tensor on a Kähler manifold, that deformation is always unobstructed.
I think so. I don't remember the details. I didn't prepare this part. I just wanted to put kind of a remark that.
Well, my understanding is that Goto proved this in the generalized scalar setting, and Hitchin find a completely analytic proof without generalized scalar geometry at all, the same fact. But yeah, it says that the direction is unobstructed.
Right.
But it's not like a statement about GK structures at all. It's just that when you say unobstructed, you mean as a deformation of complex structure.
Yes, the initial result of Goto was for generalized scalar, but as a consequence, as a corollary, you get unobstructedness of the complex deformation. And I think Hitchin rewrote this in a purely complex analytic framework.
Maybe it's helpful to say that. So what Goto proved was that if you have a pair, let's say if you have a generalized scalar structure and you have one of the two is either symplectic or what he calls having a pure spinor, so meaning that it has a trivial canonical bundle, the generalized complex structure. So the symplectic case is a good example of that. Okay, so one of them has this symplectic type nature or a pure spinner. The other one, if you deform it, the other one, then the symplectic type one can be modified to maintain compatibility. So he called it a stability theorem. If you deform one of the GC structures, then the other one can be deformed along with it. Okay, but he needed that assumption that it has a pure spinner or is of symplectic type, that second one. Now, the thing about Hitchin's result is that, as you said, it's only about holomorphic Poisson structure. So it's basically saying if you have a holomorphic Poisson structure, and if you give me a 1-1 type form, then we get an unobstructed deformation of holomorphic Poisson structure. Okay, so then what I showed was that no matter what generalized Kähler structure you have, right? It doesn't matter what the type is, it's completely irrelevant. There's always a pair of holomorphic Poisson structures. And the point is that if one of those holomorphic Poisson structures is unobstructed in a certain direction, then the rest of the GK structure goes along with it. So it doesn't depend on any stability type theorem, and it doesn't depend on the other structure having, in fact, it doesn't care about either one of the GC structures because you're not deforming the GC structure. You're only deforming the holomorphic Poisson structure. So you're using the holomorphic Poisson structure as a guide to try to deform the rest. So it's a completely different, it has an overlap with Goto's result, but it's totally, but it also has a non-overlap, and also the type of deformation considered is completely different. What he's doing initially is deforming a GC structure, and he's repairing the second one. What I'm doing is deforming a holomorphic Poisson structure and deforming the metric. It's very confusing because there's all these different levers. The structure can be interpreted in different ways, and there's many levers that you can use to deform. But I think that the holomorphic Poisson deformation, the one that I'm talking about, I think that one is the one that shows up in your papers, Jeff. Like this thing about the flow construction, right? For some reason, it's that kind of deformation which is showing up in your papers.
Yes, yeah, that's my understanding.
But I mean, it's important to remember that this type of deformation is a very special type, the one that is the holomorphic Poisson deformation. Like there's these directions that are unobstructed, but that says nothing about, you know, potentially a lot more deformations. It's kind of like basically like in my paper with Francis, right? We're taking the view that a generalized Kähler structure has an underlying holomorphic structure, which is an object in Poisson, holomorphic Poisson geometry. And then on top of that, we have some additional smooth data, which gives the metric. And so what I've been looking at is deforming that holomorphic substructure. So you deform that Morita equivalence, deform the Poisson structure, right? And then the question is, can you deform that additional smooth structure along with it? But it's definitely like it's a privileged point of view where you view the holomorphic Poisson substructure as being like the analog of the complex structure of a Kähler structure.
Please, Francis, go ahead.
Okay. How long is the?
Well, yeah, we never are somehow very rigid. If there's a natural stopping point ahead, or if this is it, that's fine. It's up to you, I suppose.
Let me just say one more thing. Well, is it okay if it takes maybe 15 minutes?
Francis, aren't you giving a second talk?
That's true, yeah.
Yeah. So in any case, I guess, yeah, 15 minutes is okay, I suppose.
I'll just give a preview for the next talk.
Okay, yeah.
I'll try to. Right. So I want to, yeah, so I want to now kind of switch gears towards describing how you can get to the generalized scalar potential and what the kind of the right perspective is. So I'm just going to briefly explain the kind of the prototype, which is an idea that is due to Donaldson. So he gave a reformulation of Caylor geometry as a Lagrangian submanifold of a symplectic manifold. So I'm just going to describe this, and that will be the kind of the preview for next time. So if we start with a Caylor structure, there's 2 steps. So step 1, step 1 is that the Caylor class which we can view in H11 or H1 of omega 1, it defines an affine deformation of the cotangent bundle. So here's how we can construct this affine deformation. So we start with a cover. Then on each of these open sets, we choose Caylor potentials. So that means that omega restricted to ui is I d bar ki, and we can rewrite this as a d bar of minus I d ki. So I'll call this quantity ai. So that's a 1-0 form. Then on the difference, on the overlap, we have aij, which is ai minus aj. So now this is going to be closed and holomorphic. This is closed, holomorphic. And what this is, this aij, it's the Czech representative of the Caylor class. And what we do is we view aij as transition data. So as transition functions for an affine bundle modeled on the cotangent bundle. So if we draw a picture of what's going on, here we have a piece of the cotangent bundle. So this is like T star of ui. We have another piece, T star of uj. And then we have the overlap region. So it's a transition function. So we take a 1 form and we send it to the 1 form plus aij. So when we do that, the result is that we get a new space Z, which is obtained by gluing all these cotangent bundle pieces together using these. And the result is that we get, this is an affine bundle for the cotangent bundle. So we can kind of add cotangent vectors to elements of Z. And because Aij, this is closed, that means that this transition function here is actually preserving the natural symplectic structure which exists on the cotangent bundle. So the fact that Aij is closed, this implies that Z inherits a holomorphic symplectic form, which I'll call omega. Okay, so this is the first step. The Kähler class, it corresponds to a holomorphic symplectic manifold, which is an affine bundle for the cotangent bundle. Step 2, so step 2 is that the Kähler metric, it defines a, well, what I'll call a brane section L inside of Z omega. So here's Z. It has these kind of vertical fibers. And we want to define a section of the projection. So the way that we do that, well, remember, we had these AIs. So we have the AIs, which is locally minus I dki. So initially these are just different local sections, but on this space Z, they glue. So these glue. These now glue to a global section, which I'm going to call L of Z. So if we want, we could call the map the kind of the section L. Or, I mean, sometimes I'm just identifying it with this image. Okay, so we get, yeah?
The complex structure on Z is somehow compatible with this T star M action, or?
Yeah, exactly. It's a holomorphic action.
Okay.
That's, yeah. Yeah, so, okay, so let's look at the section. So what, I mean, what's basically the only thing we can do? We can take this holomorphic symplectic form and we can pull it back by L. Notice that L is not going to be holomorphic. It's just some C infinity section. But we can pull back omega, and locally it's the same thing. I mean, because this was built out of pieces of the cotangent bundle, it's the same thing as restricting the canonical symplectic form on the cotangent bundle to the graph of I dki. And I mean, this is the kind of the defining feature of the canonical symplectic form, that if you pull it back by a one form, what you get is D of the one form. So in this case, we get omega, we get the Kähler form. So this is real. So what this tells us is that, well, first of all, L it's a Lagrangian for the imaginary part of omega, right? Because the imaginary part vanishes, but it's symplectic for the real part, right? And in fact, well, so these two properties, these we kind of, the fact that it's Lagrangian for the imaginary part, this is what's called being a brane. L is a brane. Sometimes people use the terminology that L is an LS submanifold, because it's Lagrangian for the imaginary part and symplectic for the real part. But the upshot of all this anyways is that L recovers. So L allows us to recover the metric. Or another way of saying it is that it encodes the metric. L encodes G, and it gives a global meaning for the Kähler potential.
Sorry, Francis.
Yeah.
I lost track of big omega versus big omega 0. Okay.
Sorry. Yeah. So big omega 0, this is supposed to be the symplectic form on the cotangent bundle. So yeah, so it's a little bit confusing how I wrote it. So Z is built up by taking the cotangent bundle and chopping it up and regluing it. And the way that it's reglued is by translations, by closed holomorphic one forms. So the fact that they're closed, it means that the symplectic form, that this transition function is symplectomorphism with respect to the canonical symplectic form on the cotangent bundle. So that means that you can think that omega, Z omega, it's a holomorphic symplectic manifold, which is not isomorphic to the holomorphic cotangent bundle in general, but locally it is. So what I'm saying is that L is kind of built up by these local pieces, which are the graphs of dki, where ki is the Kähler potential. So if we pull back omega by L, locally at least, it looks like we're pulling back the canonical symplectic form on the cotangent bundle by AI, which is the graph of dki. Does that make sense? And then the next step here is I'm using this kind of defining fact of the symplectic form on the cotangent bundle, that if you look at the graph of a one form and you pull back the holomorphic symplectic form, it gives you D of that one form. So that's the basic idea, that so we kind of encode a Kähler structure. It gets converted into this data. So this is the holomorphic data. And it encodes the complex structure plus the kind of the topology. Like it encodes the cohomology class of omega. And then the extra structure is kind of real, or it's kind of smooth, C infinity data. And this is what encodes the metric. So we can kind of, this is like another way of splitting up a Kähler structure into some underlying holomorphic data and some underlying, and some kind of smooth data. And we can kind of vary each of them independently. And this is the picture this is the picture that generalizes to the setting of generalized Kähler structures of symplectic type. So yeah, let me just, I'll end here.
Okay, sure. Yeah, thanks, Francis. Yeah. Are there any more questions? Okay, well, yeah, if not, we already had quite a few, so yeah, that was a very nice talk. Yeah. And so I guess you'll keep going next week and we'll get the rest of the story. Yeah. Okay, excellent. Yeah. Okay, yeah. Thanks everyone.
Thanks.
Thank you.